All right, so good morning, good afternoon, everybody, and welcome to another exciting program with us here at Exploring by the Seat of Your Pants. I am thrilled for a number of reasons. Number one, I'm going on vacation tomorrow. That's always kind of fun. Christmas is coming up. I've got the best sweater ever. I know a lot of you are already in festive garb, which is awesome. So a big welcome in as we get ready for the holidays and you guys get a little bit of time off. So well deserved. You kids have been so awesome this year. Speaking of this year, this is my last program of 2023. I've done over 215 of these so far at Exploring by the Seat of Your Pants, over 400, and all of them are on our YouTube channel. So if you want to check out programs with astronauts, cave divers, zoo animals, pretty much any science or exploration topic you can imagine, head there, check it out. Lots to explore and discover. And we've still got about 5 more this year with my colleague Joe. So tune in. Lots of exciting stuff. We're going live from a penguin colony in Argentina tomorrow, I think. So some really fun stuff. And a big thank you to all you amazing classes for joining us as we get to showcase and celebrate such amazing people and places. Now, today, I am so excited because a few months back, I had the chance to talk to some of the folks at If Then. I'm going to share this with all our classes. We've got some big things happening with them next year, but it is the single greatest Women in STEM campaign of all time. Every February, as some of you may know, we spend the entire month featuring solely awesome women in science. And so I got in touch with our amazing speaker du jour, Dr. Wendy Rock. So she is on all manner of social media. She is an amazing geologist, science communicator of many decades of experience sharing the wide and wonderful world of the world. We don't really feature geologists that often, so it's a real thrill to get to talk about a new scientific topic for many of you. And a big thank you for all our classes today. Ms. Richardson, Ms. Holben, Mr. Coddington's class. You guys just joined us a second ago too, so welcome into everybody. I am going to stop talking soon. As excited as I am, I'm going to bring in Dr. Wendy. She is going to blow your mind with some really cool stuff about her research, the world of earthquakes, and more. And I can't wait for all your questions. Now, Wendy, welcome to the broadcast. Nice to have you on for the first time. This is so exciting.
I'm so excited to be here, and I'm so happy to talk to all of you today about my favorite topic, earthquakes.
We have over 500 kids tuning in from literally like coast to coast, Alaska to Florida, like California to Nova Scotia. We're like crossing the continent. So I know you've got a lot to share. If you want to dive in, bring up your like awesome presentation. We're so excited, and we'll get underway.
Okay, here we go.
Perfect. And voila, we are golden. You are good to go.
Perfect. Well, hi again, everyone. Again, I'm Dr. Wendy Bohon, and I am an earthquake geologist. This picture here is a picture that I took of the San Andreas Fault. That's probably the most famous fault in the world, and it runs through California. So science is about asking questions. As an earthquake geologist, these are some of the questions that I ask myself every day. The first thing I always ask is, where are the faults? Because earthquakes happen on faults. So if I want to know where earthquakes are going to happen, I have to find the faults. I want to know how often there are going to be earthquakes on those faults, how big those earthquakes can be, when the next earthquake might occur, and what effect those earthquakes might have on people or the things that we build, like houses and schools and roads. And so how do we think about these questions and how do I answer them? That's what I'm going to talk about today. But first, we have to talk about something a little weird. We have to talk about how the Earth is like a hard-boiled egg. So everybody's seen a hard-boiled egg, right? It has different layers. It has a shell. It has the white part. It has the inside yolk. The Earth also has layers. It's a little more complicated than the inside of an egg, but the part that is most similar is that thin outer layer. Okay, so a hard-boiled egg has a shell, right? And what is the shell like? It's very thin compared to the size of the egg, and it's brittle, which means it can break. The Earth has a crust. It's very much like the shell of the egg. It's also very thin compared to the size of the Earth, and it is also brittle. And in fact, it is broken up into big pieces that we call tectonic plates. This is a map showing different tectonic plates, and you can see them in different colors. Now, these plates are moving around very slowly over the surface of the Earth. And the places where those plates touch each other are the places where we have the most earthquakes. So this is a map, and all of these flashes are showing different earthquakes. And if you look carefully, you can see that the outline of those earthquakes, the places where they occur, Those show where the tectonic plates touch each other. About 80% of the world's earthquakes happen along these tectonic plates, maybe even a little bit more. Some earthquakes, though, do happen inside of the plates, away from those boundaries. So everywhere can have an earthquake or feel shaking from an earthquake. And so that's the first thing I want to know, right? Good. The best place to look for earthquakes and faults is along the borders of these tectonic plates. But I also want to know how these tectonic plates are moving. And we can use tools to help us figure that out. So who's ever heard of a GPS? Anybody? Raise your hand. Most of you have, right? You might have one. If you have a phone, you might have a GPS in there, or you may have been in a car that has a GPS. We use GPS in science as well, but the GPS that we use is much more accurate and sensitive. And so do you see that instrument on the left there? It looks like a R2D2 with really long legs. That is a GPS instrument that we use for science to help measure how the crust of the earth is moving up and down and side to side. Now, the map over here on the right is showing the location of hundreds and hundreds of these GPS stations in Western North America. So you won't be able to see it, but you see all those red arrows? The end of every arrow, trust me on this, there's a little black dot, and that's the location of one of these GPS instruments. Now, the arrows are pointing in the direction that the crust is moving. And the arrows, when they're very short, that means the crust is not moving very quickly. And when the arrows are long, that means the crust is moving very quickly. But something I want you to look at, if we look over here in Utah, can you see that you can barely see those arrows? And the ones that you can see are moving very slowly to the west. But if you look in California down here, those arrows are moving in a different direction and they're moving very quickly. That tells us that there's a big difference in how the ground is moving in those places. So here's a cartoon showing some of that. Here's two different GPS stations, and imagine they're moving apart. That tells us that there is something happening in between those GPS stations, and what we need to go and look for are some faults that are there that are helping the ground to move in these different directions. So that gives me, a geologist, another clue of where to look to go find a fault. Okay, so now we've looked along the plate boundaries. We've figured out that in between some of these GPS instruments, the ground's moving differently. And now we can use another kind of technology called LIDAR, light detection and ranging. This is basically a laser, okay? But not like a lightsaber laser or a laser you'd use to cut something in half. This is more like a laser that you'd use to play with your cat. It doesn't hurt anything. We put a fancy laser in the belly of an airplane or a drone or a helicopter, and then it flies back and forth scanning the ground. And as that laser scans the ground, it helps us to make a three-dimensional map of the surface of the ground, just like it's showing here. So it'll show us things like trees and buildings and roads and faults. So this is what a LIDAR image looks like. This one is from Northern California. Now let me explain what you're seeing. Do you see the rough knobbly part that looks almost like popcorn? Those are the tops of trees. And now you may see something down here, a little squiggle cutting through. That's a road. And if you're looking really carefully, you may even see a square down here. That's a field for horses. There's a barn, there's some other houses. So this is what the LIDAR images look like. And the San Andreas Fault is running through this image. The problem is it's underneath those trees. So how are we supposed to see it if it's underneath the trees? Well, luckily, the laser is a lot like sunlight. So have you ever stood in a forest underneath the trees? The trees will block a lot of the light, but some of that sunlight filters down and hits the forest floor. Do you know what I mean? So when the laser is scanning back and forth, sometimes those laser pulses will come through and hit the forest floor. If we only look at the ones that hit the ground, we can take the trees away and see what the surface of the ground looks like underneath of them, which helps us to use clues in the landscape to figure out where exactly the fault is. And I've drawn the location of the fault here. Okay, so now we know where the fault is. What can we learn from that? Well, now we want to know how big earthquakes that had happened there in the past were and how often they happen. To do that, Oh, you can put the trees back too. We don't actually hurt any trees. We don't want to do that. We have to preserve and care for the earth. So when we want to figure out what's going on with the faults, we will dig down into the fault itself. So dig across it. Why in the world would we do that? Well, it turns out that the rocks hold clues to the mystery of the earth. So if you can learn to read the rocks, you can really understand the history of the earth. These types of rocks are laid down flat. And so if these rocks are no longer flat, that means something has happened. And in this case, that something are many, many earthquakes. So we dig into the ground so that we can see what the rocks are telling us. And this is what it'll look like inside that fault trench or the hole we dig. Now, I put the colors in here to make it easier for you to see the types of things that I'm looking for when I'm in this trench. So this red line that you see, the really thick one, that's the San Andreas Fault, you guys. That's what it looks like inside the ground. It's not a hole that opens up. It's like a zipper almost. And all of these different lines were different layers of rock that had been laid down and have been moved by earthquakes. So if we look at this blue line and follow it across, it sort of disappears. And let's say we look at the purple line, we'll follow it across, it disappears, but we can find it again down here. All of these are clues about what happened in the past. We can take these clues and then we can also date some of the parts of these rocks, and that tells us how many earthquakes there were that we can see right in this little area and about how often they happened or how far apart they happened. And if we can learn those things, we can figure out when the next earthquake might be likely. But I haven't even told you guys what an earthquake is yet. Silly me. Let's talk about that. Okay, most people know intuitively, what an earthquake is. It's when the ground shakes, right? But what does that really mean? Okay, so I want you to think first in your mind, shut your eyes. Imagine you're holding a pencil and you're bending the pencil really slowly. It bends, but then it starts to sort of crack and eventually it will break. Okay, open your eyes. That's exactly what's happening with earthquakes. We have the tectonic plates that are moving and they start to bend the rock. They're applying stress and strain to the rock. And eventually that stress will build up until the rocks break. When they break, they send energy waves out in all directions. And that's what we feel as shaking. Those energy waves cause the ground to shake. Here's an example of ground shaking in Nepal, which is in the Himalayas. And this was a huge earthquake that happened in 2015. It was a magnitude 7.8. And another interesting thing, I wanted to bring this in because we had just talked about GPS, so I know you guys will understand this. There was a GPS station near where this earthquake happened, and we plotted what the movement of the ground was at that GPS station and put it inside of this white box. So you're going to watch the people and watch the white box. So the earthquake happens right now. See all the people? They can barely even stand up. And you can see that the GPS station was also recording that movement. The ground moved more than 4 feet during that time. Here it is again. But what's interesting is that even during the same earthquake, the ground doesn't shake the same amount everywhere. There's different things that change what shaking you're going to feel at the surface. So this is a map showing the amount of shaking from an earthquake that happened in California a few years ago, 2019. It was called the Ridgecrest earthquake, and it was a magnitude 7.1. The colors are showing us how hard the ground was shaking in different places. So the areas in red were shaken very severely. The areas in orange and yellow were shaken pretty hard to moderately, and then the areas in green and blue were only shaken lightly. So you can see that near where the earthquake started, the point on the surface above where the earthquake happened, because earthquakes happen underneath the ground, that area shook really hard. It's red. But look at this. There's some red over here too. And look at this yellow, how strange it is. It goes up the valleys, even though the areas around it are in green and blue. That's showing the effect of different types of rocks. So the rocks that make the mountains are hard and solid. And the rocks that make up the valleys are soft sands and soils. And this soft sand and soil, you guys, it's like jello to earthquake waves. When the waves pass through it, they get stuck in there. And so you shake harder and for a longer period of time if you're in these soft sands and soils rather than in the bedrock. So that's important too. And if you're down in these soft sands and soils and there's a lot of water, there's another potential hazard called liquefaction. Now, that is a very fancy word for kind of like quicksand, okay? You all may have experienced this. Has anybody stood on the edge of a lake or a river or the ocean and wiggled your toes in the sand, the wet sand, or wiggled your feet and had your feet sink down a little bit? If you did, you created liquefaction. Earthquake waves can do that too. In areas where you have lots of sand and soil and lots of water, when you shake the ground back and forth, it pushes water up towards the surface, which pushes apart all those little grains of sand, which causes the ground to lose its strength. And that creates quicksand just for a few moments. But if you have your house built there, that could be trouble for your home. Another thing that can happen during earthquakes is something called ground rupture. So to rupture is to break. Earthquakes start miles below the surface, but sometimes the rocks can break all the way up to the surface of the earth where we live. And if your home or your school or your road is built where the fault breaks at the surface, it can actually break your house too. So many places in the United States and around the world have laws that keep people from building structures or roads on top of faults that can break all the way up to the surface. Landslides are another thing that can happen during earthquakes. So this is a photo from California after the Northridge earthquake that happened in 1994. Now, there were more than 9,000 landslides in that part of California after this earthquake. And what happens is the ground will shake in areas where you have steep slopes. And if you've had a lot of rain, or maybe there's been a wildfire or some construction nearby, that slope may not be sturdy and stable. And so the earthquake shaking can cause the slope to collapse in a landslide. And now all of these things can happen in different places. So this brings up another thing I want to talk about. But first, let's talk about this map. So this is a map from the California Geological Survey that is showing different hazards from earthquakes. So this whole area could have earthquake shaking, but it could cause different effects in different places. So up here, this is the area, so Malibu is right down here, and these are the San Gabriel Mountains, and they're very steep, so they can have landslides, and that's what we're seeing in blue. These areas down here in green, these actually used to be swamps before the city of Los Angeles was built on top of it. So this is an area that has a lot of water. What happens when we have a lot of water and soft sand? Liquefaction. So this is an area that can experience liquefaction. And across here, these yellow boxes that have the dots in the middle, those are places where we know that earthquakes have broken the ground, the surface of the earth in the past. So it's likely to happen there in the future. So if you live in this part of Los Angeles, you have a lot of different kinds of hazards, but depending on where you are, you may or may not be at risk. So what do those two things mean? A hazard is something that has the potential to harm you, like a shark in the water. Risk is the likelihood of that hazard causing harm. So if the shark is in the water and you are on the land, the hazard is still there, but your risk is very low. You're not likely to be hurt by the shark. And so what I do, a lot of what I do is try and understand earthquakes, understand the hazard, and then talk to people about how they can make their risk lower. The things that they can do to make themselves, their home, and their family more safe. So if you live in California or other places where there might be earthquakes, it's at the west coast of the US and some places in the East Coast and the Midwest, these are a few things you can do. You can secure items in your home. You can have a family plan. You can make sure to have emergency supplies. You can make some change some things about the structure. And this is one thing I want to talk to you all about. Do you know what to do if you feel the ground shake from an earthquake? You drop down to the ground, take cover underneath a sturdy object like a desk or a table, and then hold on to that desk or table until all the shaking has stopped. We say to do that because in the United States, most people are injured by falling objects. And so if you're underneath a table, objects are less likely to hit you. So then after the earthquake, you want to make sure that you clean up anything that could be a problem or a danger, and then go out and talk to your neighbors, check with your friends and family to make sure that they are also okay. So you may have a hazard like an earthquake. We're never going to be able to stop having earthquakes, but there's a lot that we can do to make sure that we lower our risk so that we are not likely to be harmed by the hazard like the earthquake. So if you're interested in this sort of stuff, you can find me at my website. If you have any questions, I'm happy to answer those. Now, here's a few pictures of me doing my thing. So I work all over the world. These pictures are from Argentina, Bolivia, and India. I also do a lot of work in the laboratory, doing different kinds of geochemistry. So understanding more like the whispers of the rock, the things, the secrets that are held in their chemicals. I do a lot of talks to lots of different people about why science is important. And I do a lot of things on TV and radio to make sure that I can talk to as many people as I can so that they know what to do when they feel an earthquake. All right. I don't know how to.
Oh, all good. Wendy, take your time. Come out of screen share. It's a little finicky. There you are. That was amazing. Thank you so much. I mentioned at the very top of this that you've been doing science communication in a wide variety of avenues for many years now, and that was the slick of talk as I've seen in a long time. So thank you for that very much. We're going to dive in with questions. We've got tons of time for Q&A because Wendy rocks and was like the most on-time person of all time. And so we are going to dive in. There's some YouTube ones that are coming in that are spectacular. So I'm going to start with those, give our live classes just a second to get their thoughts together. But Miss Barajas, I'm coming to you in a minute first, so stay tuned for that. Miss Spires Group joining us, Rutland Middle School. Carter wants to know a great question, which I'm sure you get all the time. Are there architectural ways to stop earthquakes from breaking down buildings? How do we build resilient structures?
Excellent question, Carter. There's lots of people working on this too. And there's lots of different ways that you can do it. The Japanese really have the most innovative ways of doing it. There are different pendulums that you can build into buildings to help damp down the shaking. You can actually build buildings on rollers so that they don't shake quite as much and damage things. But for normal people that are not living in these big high-rise buildings, there are things that we can do too. A lot of times we have a foundation of a house and you build the house on top of the foundation, but earthquake shaking can cause the house to shift right off the foundation. So we have to make sure to secure the house to the foundation. That can help. We also want to put in what's called a shear wall, which means, so the earthquake moves the ground in different ways. It gives it an upwards push, a sideways thrust, a downward drop, and a sideways push in the other direction. It also can make a rolling motion, which is really hard for houses. And so if we can add in sort of X's, shear walls in between, like the different, if you have a 2-story house or whatever, there are things that you can do to add in some strength and stability. So there's lots of stuff you can do.
How cool is that? Thank you, Wendy. You mentioned mass dampers at the beginning. Everyone should look up the tuned mass damper in Taipei 101, which is one of the coolest things inside a structure in the world to specifically guard against earthquake damage. So really, really cool building for everyone to check out when you're done this broadcast. I'm going to take one more quick one from YouTube. Live classes. I am coming to you live. You don't need to share in the chat. It'll be much easier when we go that way. So stay tuned. I am coming in a minute. Miss Tomash's class in Alaska wanted to know how many earthquakes are there in a year, every year around the world. Is there a figure on this or what do we know?
Yeah, that is an excellent question. And since you're from Alaska, I'm going to address Alaska first. So when we have more seismic instruments, we can record more earthquakes. And recently there were a lot of seismic instruments installed in Alaska. And now there are about 11,000 earthquakes recorded in Alaska every single month. Okay. So there are hundreds of thousands to millions of earthquakes that happen around the world every year. Most are too small to feel. We can just detect them with sensitive seismometers. So millions of earthquakes, so many earthquakes.
Wow. It's way more than I would have thought. Thank you for that. I like being surprised in these broadcasts. We do a lot of these. So that's fantastic. Great question, guys. All right, we're heading to Miss Barajas' class, Oxnard, California. I'm coming to you, and then our Mighty B Academy friends with Miss Kim in a minute. Come on in, Miss Barajas. Hey. Hello, California. Come on and ask a question for us.
I have a question. What was the world's biggest earthquake?
Yes.
That is a great question. So we only know the earthquakes that humanity has been around for, right? So we can't say the biggest earthquake in the history of the world, but the biggest earthquake we've ever recorded was a magnitude 9.5 that happened in Chile in 1960.
Yeah. Now, on a 9.5 note, I want to clarify something for our kids now. Like a level 9 earthquake is not like a little bit bigger than a level 3. Like, is there a way to sort of quantify this for our kids that might not know this scale?
Darn it, I don't have my pasta earthquake with me, but if you imagine one strand of spaghetti, okay? One strand of spaghetti, if you break it, let's think of that as a magnitude 5 earthquake. To get up to a magnitude 6 earthquake, you would have to break 32 strands of spaghetti because it's a logarithmic scale, which means that every earthquake is 10 times bigger in its waves, but it releases 32 times more energy. So
Wow.
32 strands, which is like a whole serving of pasta. Imagine breaking 32 strands. So to go from a magnitude 6 to a magnitude 7, that would be 32 times larger, okay? So that would be 1,024 strands of spaghetti, which is bigger than my head. I can't even get my hands around that many packs of spaghetti. It's like 3 or 4 boxes of spaghetti you would have to break. And to get from a magnitude 7 to a magnitude 8, 32,000 strands of spaghetti.
Wild. I love that analogy. That's a spectacular thing. By the way, 1,000 is about my serving of spaghetti, just so you know. You went very low with the 30. I don't know. But great question, guys. All right, Miss Kim, come on in. Mighty Bee Academy, our 4-5s from the virtual school all around the U.S. If you want to flick on your camera, your mic is good. Come on in, Miss Kim.
Hello. Yes, one of my students would like to know, how long does an earthquake normally last, and what is one of the longest ones?
Cool.
That is a really good question. So earthquakes, we see them as dots on a map. And so it looks like they'd be kind of like an explosion, like bang, and they'd be done. But really, earthquakes are like zippers. So small earthquakes don't take very long. Imagine unzipping like the zipper on a little shirt, zip, and you're done. And that would be a small earthquake that would only shake for a few seconds. But these larger earthquakes, like the magnitude 9.2 Tohoku-oki earthquake that happened in Japan, that was a magnitude 9.2. That would be like unzipping a sleeping bag. So it takes a really long time. And shaking from that earthquake lasted several minutes.
Wow.
So most earthquakes are very short, just a few seconds, 1 second to 10 seconds to maybe 30 seconds. But these really big earthquakes can last for minutes.
I love that you showed the film of Nepal too. I've never seen that action so illustrated before. I've seen the aftermath when tsunamis coming in Japan. That was the sort of biggest earthquake that a lot of us will have seen footage of, or a lot of footage of. But the Nepalese one was fascinating. So great question, Miss Kim's class. All right, Miss Brenda, I know your audio's off. I'm going to bring you in to say hello. So nice to have you guys, Mighty Bee again, grade 1 through 3. So cool that there's so many kids tuning in from you guys around the US. And your first question for us, let's see, Samuel wants to know, how do you help a person when an earthquake happens, Wendy? Is there some tried and true technique?
That's a great thing. So how I would help a person is by giving them information about what was happening and what they can expect to happen next. How you could help a person in an earthquake is to check and make sure if they're injured and to see what they need. So if you're in a place that could have earthquakes and you know that you and your family are safe, you might want to go around and check with people in your community, see if they need water, if they need food. People will usually come together after things happen like earthquakes and share resources. So, see how you can help out in your community, how you can help out your caregivers, the people that you live with, make sure that they don't have any injuries and help them to clean up anything that could be dangerous around the house.
What a nice answer, and true for a lot of natural disasters. This isn't true of just earthquakes. If you're in trouble, help out people in need, make sure you're safe yourself, and then go from there. Great question, guys. All right, we're going to head to Miss Coddington's class. We've got Miss Coddington, Miss Richardson, Miss Holman's class. We're going to take some from YouTube. We've got tons of time. Wendy's like the fastest Q&A answer of all time, so this is fantastic already. Miss Coddington, come on in, guys. Hey.
Where in the world do earthquakes happen the most?
Oh, that's such a good question. And I have a lot of these answers actually on my TikTok. So I know this because I just researched it. It depends on what you say when you mean like the most. So most earthquakes happen around what we call the Ring of Fire, which is the area around the Pacific Ocean. And that's because that Pacific plate is moving really fast. So Japan and Indonesia tend to have the most earthquakes. Japan has more than 100,000 measurable earthquakes every year. And on average, people in Japan feel earthquake shaking every few weeks. And if you're thinking about like just the size of a place, there are island nations like Tonga and Vanuatu that feel earthquakes pretty often, including big ones. They've had I think they've had now 8 magnitude 7+ earthquakes just this year.
Wow, that's ridiculous. And we were talking about volcanoes just a few weeks back, and Tonga had a really huge volcanic eruption in the not too distant past as well. So interesting places to go visit, interesting places to live. I'm glad I don't feel earthquakes every few weeks. That would be kind of a little alarming, but I guess you get used to it like everything else. American sort of central south tornadoes are part of the landscape. Like it's something that happens and people just get sort of used to and prepared for and account for in their daily goings on. So great question, guys. All right. Miss Richardson, we're going to head to BC. Miss Holman, I'm coming to you guys next. And then we've got a whole bunch more on YouTube. Come on in, Miss Richardson's class. If you want to flick on your mic and camera, we can check in with you. Let's see. Maybe. Oh, there we are. Hello. Welcome in. Hi. Hello, everybody.
It's a big class, man. It's a big class. It's 28 people in here.
28 people.
Yeah.
Okay. We have some questions. Our first question was, what would you do if there was an earthquake and you were in a house with no furniture? Where would you go?
You would get away from all of the windows and go towards an interior wall. So that would be like a place that doesn't have anything that could fall on you that's near the inside of the house. And then you kneel down on the ground and cover your head and neck. So we want to make sure people are not falling down, and we want to make sure that anything that falls on you doesn't injure the most important parts, your brain. So cover your head and neck. That's a great question.
Great question, Miss Richardson. We will come back for a second, so stick around. I promise. So nice to meet you guys. It's awesome that you're in today. Miss Holden, we're going to go back to Guardian Angels. If you guys want to unmute your mic, you are good to go. Welcome in.
Hi, can you hear us?
Yeah, you're perfect.
Okay, we have 2 questions. One is, if you're in a car and an earthquake happens, what would you do? And I'm curious if earthquakes have become more common with global warming, or if global warming doesn't really impact how often earthquakes happen.
Both great questions. So people often experience earthquakes when they're in cars, and once they usually don't notice unless it's a fairly large earthquake or it's generating a lot of shaking near where they are. In that case, they think it's a flat tire. And so most people do what you should do. They pull over to the side of the road in a safe location. So if you're in a car and an earthquake happens, get away again from anything that could fall on you, like an overpass or power lines. Pull over to the side of the road and wait for all shaking to stop. Now, climate change is a threat multiplier. It makes many other hazards more likely and might happen more often, but earthquakes are not one of those. Thank goodness. Earthquakes start miles below the surface of the earth, and so they're relatively unaffected by just about anything that happens up here, with the exception of a few specific things like building dams or injecting water down into the ground.
Yeah, very, very cool. Great question, Miss Holden's class. All right, we're going to head to one on YouTube, and then Miss Coddington, I'm coming back to you. Mighty B, Richardson, Holden, we're coming back to everyone. I swear, we got 10 more minutes together. This is the best Q&A ever. Miss Mason's class, or Ryan in grade 3, Stittsville, Ontario, wanted to know how the GPS units you showed are made. So the tools that we use to understand these things, anything you can share on that?
You know, that's a really good question. And I don't know the answer to that, but I would be happy to look it up for you. And you can explore more about that yourself. There is an organization that handles all of the scientific GPS, or most of it, for the US. I used to work for them. There's a geodesy and a seismology side. I worked on the seismology side. But that organization is called EarthScope. And so if you go to EarthScope, they can give you all kinds of information about how the GPS units are made, where they're located, and you can actually go and look at that data in real time. So you can see how the GPS stations around the world are moving in real time.
How cool is that? Thank you for the pivot. It's fantastic. Miss Coddington's class, we're coming back to you. Come on in. You got a student right at the camera. Hello.
If you were an astronaut, can you see an earthquake from space?
Cool.
Wow, that's a good question. If it was large enough, the earthquake was large enough, you could potentially see the effect of the earthquake on human structures, but not the earthquake itself. So what I'm thinking of specifically is if there was an earthquake in a place where there were lots of people and it was nighttime. So let's say it was the part of LA, right? And you're in the space station and it's night and you're looking down and there was a big earthquake. It would knock out all of the power probably across Los Angeles. And you would be able to see that part of the world kind of go dark, but you wouldn't be able to see the cracks in the ground itself.
Yeah. What a cool question. Have you gotten that question before? That's a really
I've never gotten that question before, but I've thought about it. So
there you go. You're prepared. This is the joy of being a science communicator. You can think of weird queries that you might get. Way to go, Miss Coddington's class. All right, Miss Brenda, I'm going to bring you in to say hello, and we're going to take a question again virtually. Thank you for sharing from Paisley. Wanted to know, is there a state that has the highest likelihood of getting hit by an earthquake? We've got students from all over the U.S. in Miss Brenda's class. Any sort of worst place to be, quote unquote?
Well, Alaska has the most earthquakes of any U.S. state. It's followed by California. California has, on average, about 14 earthquakes every day. Most of them, again, are not felt. But what's interesting is there was a period of time in about 2009 to 2015 where Oklahoma had more earthquakes than California. And that was because they were man-made earthquakes that were a result of activities that were being done by energy companies. So anywhere, I'm doing a whole series on TikTok and I'm putting them on my YouTube channel about earthquakes in all 50 states. So I'm going in alphabetical order. I'm doing Hawaii later today. So if you live in any states and are interested in knowing about the past earthquakes that have happened in your state or where earthquakes are most likely, check my YouTube channel because I'm talking about every state. And even though not every state has earthquakes very often, every state does have earthquakes.
Fascinating. I want to clarify something because I'll bring it up on camera and share it with our classes. On TikTok, your Dr. Wendy rocks it. Yes?
Mm-hmm.
Perfect. Okay, so I'll bring this up. I'll share it with our classes as well. You can check her out there. Lots of stuff. And you're just Dr. Wendy rocks on a lot of the other
everywhere
channels.
else. But they didn't let me have that handle on TikTok. Darn it, TikTok.
We're going to write them a letter and be angry together. Miss Kim, I'm going to head to you guys. If you want to unmute your mic, come on in and share a question on behalf of your kids. Hey.
Yeah, Bella wants to know if there are earthquakes in space.
Yes.
Oh, Bella, what a good question. So there are not earthquakes in space exactly, but there are moonquakes and Marsquakes. So we have the rocky planets. Do you guys remember the rocky planets? So we have Mercury, Venus, Earth, and Mars. And then we have the moon, which is our satellite, right? All of those are rocky. And so there are forces that are acting on them that cause their rocks to break. They are not necessarily tectonic forces like earthquakes on Earth, but there are rock quakes on Mars and the moon. And we assume also on Venus and probably Mercury, but we haven't measured them there. In fact, we've had seismometers on the moon, and NASA recently put a seismometer on Mars called SEIS, and it recorded Mars quakes that were as large as a magnitude 5.
Wow. I didn't know that. How very cool. Wendy, this has been so, honestly, like, professional detachment aside, I always have fun with these broadcasts, but I've learned so much in this one. This has been particularly fun for me, so thank you. We're going to head to Miss Richardson's class. If you guys want to unmute your mics and come on in. Miss Holman, I'll come to you last after a couple more on YouTube. We've got like 4 more questions we're going to do together. This has been like the longest Q&A ever. I love it. Welcome back, guys. Hi.
We are wondering when the first ever earthquake was recorded.
Okay, this is a kind of a hard question. So there's something called a seismoscope that's not really a seismometer like the earthquake machines that we use now. And it was made in 123. I think it's 120. It's either 132 or 123 AD. So thousands of years ago, it was made in China. And what it looked like was all of these beautiful dragon heads, like holding a marble in their mouth. And underneath each dragon head, there was a frog with its mouth open. And the idea behind this is that when there was an earthquake, that first jolt, the push, would knock the marble out of the dragon's mouth and into the frog's mouth. And that would tell people which direction there had been an earthquake in. So they would figure out where the earthquake had come from, more or less, but they didn't know where exactly, and they didn't know how big it was. So we knew where there were earthquakes happening. And people have been writing about earthquakes for thousands and thousands of years. In fact, you guys heard of Socrates? Socrates talked about earthquakes, but he said that he thought that earthquakes were caused by the wind whipping around in underground caverns. Now, we know that's not true. Now we know more things, but earthquakes have been talked about for a really long time. The first earthquakes that were recorded by seismometers, like the kinds that we have now, like by Charles Richter and others, a lot of that work was done in Japan in the late 1800s.
Wendy, that was like the most detailed answer to a question that I would have thought that no one would know offhand I've ever heard. So thank you for that very, very much. We're going to take 2 quick ones from YouTube, rapid fire round, and then Ms. Holden, we're going to wrap up with you again at the 40-minute mark. I just want to note for our classes, Wendy is everywhere on social media. She's got a YouTube channel. She's on Instagram, Twitter, Facebook, TikTok, everything. You can check out her amazing website. You can check her out on all sorts of social media platforms. And as we said, on TikTok at Dr. Wendy Rocks It when you're done this broadcast. If you want to find out more, you can only take so many questions in one broadcast. It's our one shame here. But let's take 2 from YouTube before we wrap up. Let's see. Oh, Mr. Mash's class, what number does the earthquake scale go to? How big do we get? 9.5 is the biggest.
Great question. It goes to a magnitude 10, but we cannot have an earthquake of magnitude 10 because we don't have any faults that are long enough and deep enough to release that much energy. So we think probably the highest magnitude earthquake we can get is around that 9.5 level, but it does go to a magnitude 10. But this is a weird thing. It actually you can have negative magnitudes, which is weird because Charles Richter made it up. He made up the scale and he did it based on stars in the sky, the brightness that astronomers use to describe stars. And so the way it works out with the math, you can actually have like earthquakes that are a negative magnitude that are little teeny tiny earthquakes.
That's if you stomp up and down really loud at the end of this broadcast and your excitement, you'll cause a negative earthquake. You can do that in the class. That's my permission, granted. Jonathan wants to know how deep earthquakes go. And then Miss Holden, we're coming to you.
That is a really good question. So earthquakes only happen if the rocks are still brittle enough to break. So if you think about chocolate chip cookies, when you pull them out of the oven, they're gooey and bendy, they don't break. But when they get hard, they break. So when rocks are moving, they have to be hard enough to break. And if they go too deep inside the earth, they get too hot to break. So the deepest earthquakes that we see are around 600 kilometers deep. I think that's probably around the deepest. So pretty deep around subduction zones, but still only a fraction of the size of the earth.
The best analogy ever, and you can speak to this too, is that if you had an apple, it's just the peel of the crust, right? Like the most of the earth is the innards of the apple, and like we are on this thin little film that's on the outside with this thin little film of atmosphere around us. It's one of the coolest things in science discovery ever. So I'm so glad we got that question. All right, we are going to head to Ms. Holden's group to wrap us up. Come on in, Guardian Angels, unmute your mic, and we'll take one final question from you guys. You are good to go. Hey.
We are wondering how many tectonic plates there are in the world.
Yeah.
Oh my gosh, there's a lot. So I think it's about 16 of the really big ones, but then there are other little microplates. So there's a microplate off the coast of Washington called the Wanda Fuca plate. And there's even a smaller little plate off the coast of Oregon and Washington called the Gorda plate. So you can kind of break them down smaller and smaller, but if I had to guess, I would say between 30 and 40 total tectonic plates if you count all of those little microplate slivers.
Interesting. Thank you, Ms. Holden's class. And Wendy, this has been so much fun. This is honestly the best possible broadcast to wrap up 2023 for me in. So thank you more than you know. I started this broadcast by highlighting the If Then collection. I really encourage our classes. Check that out. I'll email it to all of you in just a minute, along with everything that Dr. Wendy does. You can follow up. You can check out the Hawaii video later today. Yes?
Later today. I'm going to post it today.
Amazing. Cool. Well, our classes, thank you so much for joining us today. Classes, if it's your first time joining us, and I know for some of you it is, we're going to wrap up the broadcast by bringing you all in to say a big thank you and farewell. So Miss Kim, Miss Brenda, Miss Coddington, Miss Richardson, Miss Holden, unmute your mics, flick on your cameras. Thank you so much for being here. I'll bring you all in to say a big thank you and farewell. Have a wonderful day, everybody. Bye.